Good morning, everyone. Today we have Professor Jonathan Fan from Stanford Electrical Engineering going to talk about some of the work that he's doing there on the design approaches for extreme wavefront control. He did his PhD from Harvard University, and as a junior faculty, he got almost all the awards that you can think of, including Packard Fellowship, Sloan Fellowship, and the Presidential Award for which is called PCASE, Presidential Early Career Award for Scientists and Engineers. So let's welcome Jonathan.
Thank you. Well, thank you, Arka. It's a real pleasure to be here at UW, and I look forward to telling you a bit about my work. I'd like to begin with something that everyone here already knows, which is that there have been tremendous efforts over the last few decades to basically integrate lots of components onto chips. And this certainly started with a big push in electronics and has since evolved to other areas involving, for example, MEMS devices, imaging systems, biosensors. And this level of integration using nanofabrication and microfabrication techniques has enabled low-cost advanced systems for sensing, imaging, et cetera. However, in spite of all of this, one component that has yet to be integrated using these type of methods are optics, which for a very long time, it still is the bending of light still is based on the methods of refraction as is enabled by curved surfaces. For the last 10 years or so, however, there has been a push to basically integrate these type of devices onto the stack using so-called metasurfaces. And certainly, as this technology advances, our ability to make really advanced integrated optoelectronic devices spanning the UV to the infrared can be significantly augmented. So it's the mission of my lab and the subject of my talk to understand how we may be able to push the limits of these type of devices in a manner that can hopefully enable their translation from academic study to practical implementation. Since this is my first talk here at UW, I wanted to give you a quick overview of some of the work that my group is currently doing. Certainly a major emphasis is in nanophotonic design. We're also looking into how we may be able to dynamically tune and actuate nano-optical structures using mechanics, electrochemical methods, and phase change materials. And we're also looking into new types of materials, in this case, single crystal metal on insulator, which I think can play a major role in plasmonic technologies. I also have some work in combining concepts in electromagnetics and soft robotics, which I don't have displayed here. For the purposes of giving a coherent story during this talk, I'd like to focus on some of the design methods that we're developing and also some of the material science that we're doing. And the outline of my talk is as follows. I'd first like to quickly introduce the concept of conventional metasurfaces and when they are good and what their limits are for those who may not be familiar. I'd like to tell you about this method of topology optimization to really push the performance of these type of devices, and I hope to convince you that some of these optimization methods are in fact a requirement to really enabling performance metrics that are translatable. And finally, I'd like to tell you about some of this work on epitaxy growth of metal on amorphous insulators. So to begin, as we consider flat optics as it's been molded over the last 10 years or so, most dielectric metasurface designs utilize subwavelength scale waveguides or resonators that are stitched together in a periodic lattice. So this is to say that one physical way to think about metasurfaces is as an optical phased array, whereby we have discrete components spaced by a subwavelength scale, which impart a certain type of phase shift to an incident wavefront, and that phase shift can then be used to through constructive interference to produce some form of wavefront. And in this context, there are at least two general types of design metrics that exist. Here, this is a simple toy system that was published by the Capasso group. And what we see here are two things. The first is if we consider using nanoscale silicon ridges as our waveguides, that we can ultimately tune this phase shift by tuning the width of this type of waveguide, which essentially allows you to tune the effective index. So this is to say that there are knobs within these individual discrete structures that allow you to sample different types of phase shifts. The second is that the spacing between these two structures is on the order of lambda over 2 to ensure that coupling between these structures is limited, because at least with the way these are designed, this type of coupling can be considered parasitic. As such, the way that the very general physics of these waveguides can be considered as phase arrays can be treated as follows, where we basically have highly transmissive elements where light goes in, couples into one of m different modes, where these modes are spatially discretized amongst these different elements. And then there's outcoupling. And in essence, what the transmission wavefront can be described as the constructive interference of all of these different modes as they outcouple. And there are many variations of this concept, and I think many people have developed different variations of this. A lot of initial work was actually done 20 years ago with these titanium dioxide waveguides as developed by the Lalonde group in France. And more recently, there have been some other types of waveguide structures involving, in this case, cylinders of silicon, in this case involving anisotropic waveguides with phase responses that vary as a function of geometric phase. While there are all of these variations, they all ultimately operate kind of in this type of picture where there's very strong transmission through each of these discrete elements. So this concept certainly works very well for individual wavelengths for a range of angles that are ultimately limited to maybe around 30 to 40 degrees if we're talking about devices with high efficiency. But this picture ultimately breaks down as we consider other types of limits. And as one example, I'd like to walk you through this model system, which is just one example of a number of systems where this breaks down. And in this case, what we have is an incident beam that is incident at 20 degrees, and we're looking to deflect it at a 40-degree angle, negative 40-degree angle. And the question is, what type of efficiencies can we achieve? And in this case, if we consider this periodic structure, which is to say this metagrating, the effective spacing, which is defined by these input and output angles, is on the order of wavelength, just slightly larger than a wavelength. So as we look at designing this using conventional means with nano-ridge waveguides, we can only fit two of them together. And if we fully optimize this with two waveguides that are spaced apart by equal spacings, what we find is that the best that we can do using these conventional phase array approaches is to have a device that has an efficiency of 62%. And as we can see in this plot, there's a bit of interference between the incident and reflected wavefronts here, which is to say that the impedance matching between the device and the substrate is not very good. So certainly, in this and other types of cases where we have angles that are ultimately not small or not normal, getting high efficiency can be difficult. Which raises the question of whether it's even possible using nanoscale structures at the subwavelength scale to achieve high efficiency. So to probe this with the simple toy system, we did the simplest possible numeric experiment, which is that we did a full parametric sweep of this phase space to basically understand the global phase space and to just see if better solutions exist. So we basically took this two-ridge system, we varied parametrically these widths, these spacings, these thicknesses, And here, what we have plotted is a contour plot showing efficiency as a function of thickness and spacing for the optimal widths. So this is to say, this is the compilation of many thousands of simulations. And what we find here is that there actually are patches of this global phase space that do produce quite high efficiencies, and that these patches ultimately break a lot of the rules of conventional phased array design. So in this case, we can see that this area of high efficiency ultimately has low thickness and small spacings, and that as we examine this for fixed thickness, we can see that we can get efficiencies that are much higher, in this case 96%. But as I mentioned, as we just look at what these structures look like, instead of being on the order of a wavelength tall, they're actually much more truncated. And instead of being widely spaced apart, they actually utilize near-field coupling to enable this high efficiency beam deflection. So to understand why this works a bit more, one of the things we did was we reversed engineered this, and we analyzed how it worked using coupled block mode analysis. And I'd like to spend a quick minute to explain how this analysis works. It's a general way to basically analyze and to analyze periodic structures. And the way we can frame this is that we can basically describe the interaction between an incident plane wave and a periodic metasurfaces through the excitation of block modes. So we have an incident wavefront which couples into one of n different modes. And one of three things can happen to these modes as they interact with an interface. So the first is that they can outcouple, so they can basically go out and couple into one of a number of discrete channels. And that's certainly what we have in the case of a phased array, where we have light go in, it couples to these modes, and it outcouples. So those we term the single pass terms. But it is also possible for these modes to interact with these interfaces and basically reflect back into the same mode, which we call intramode coupling, or it can scatter into different modes, which we call intermode coupling. And that introduces these multiple pass terms. So this is to say that as we consider our metasurface more as a Fabry-Perot resonator, that ultimately the way to consider the full dynamics of a generalized metasurface or metagrating is to ultimately account for these inter and intramode coupling terms as well as these outcoupling terms. And as we apply this type of analysis to our device, what we can find is that our device supports 4 block modes that are propagating. 2 of these modes have light that is strongly confined in each of the ridges, but 2 of these modes have electromagnetic radiation that's actually distributed throughout the unit cell, which is to say that these incorporate strong near-field interactions between these ridges. And as we look at the scattering matrices here, what we find is that there are strong colored terms here, both in the diagonal direction and in off-diagonal terms, which is to say that there is very strong inter and intramode coupling, and that we ultimately require this full dynamical picture to describe how this device is able to function with such high efficiency. So this is to say that while the conventional way of thinking about metasurfaces is very effective for certain regimes, breaking a lot of the assumptions that we incorporate when we design metasurfaces in this way ultimately allows us to access different areas of the design phase space and really allows us to push the performance of these devices as we start varying other metrics in different types of beam steering conditions. Now, ideally, it would be great if we can explore the full global phase space of devices in just finding regimes where these devices can operate well. But if you go beyond just, for example, periodic 2-ridge systems, doing the simulations becomes exponentially intractable. And therefore, what we really have to do is to think about this as an inverse design problem and to find other ways to basically identify these type of solutions. And there are a few ways to do this. One way to do this is with heuristic inverse design algorithms based on, for example, thermal annealing, genetic algorithms, binary searches. In these type of design methods, in essence, a series of simulations are performed, and between each iteration, a modification to the structure is made in a way where if the modification improves the figure of merit, for example, beam deflection, we can actually get higher performance. We've done some benchmarking of some of these type of methods, and they do work. Here we're trying to make a deflector where we started with something that didn't look like a grating, and throughout the course of this thermal annealing, now you can see kind of a grating emerge. However, what I will say is that while effective for certain types of devices, these type of methods require a very large number of simulations. Here, we can see this is on the order of thousands. And they are ultimately easy to be stuck in local minima, which is to say that the final devices may not optimally perform. Finally, there are assumptions to the topology that are made in terms of, for example, the number and distribution of dielectric elements. So while these heuristic methods are good, they certainly are not very optimal, and they certainly are not very computationally scalable to very large, complex structures. So that takes me to the second part of my talk, where ultimately we have identified topology optimization as a way to overcome some of these limits. Topology optimization is a concept that actually has been around for a number of decades. A lot of the original work in the field actually originated back in mechanical engineering, where people were looking to make better airplane wings and phononic materials. For the last 15 years or so, a number of people, a lot of it spearheaded by Ole Sigmund, have been applying it to make better in-plane photonic devices. And a number of other groups have been looking to further apply this largely in the context of in-plane chip-scale devices. But to the best of our knowledge, this optimization method has not really been used in the metasurface field in terms of basically transforming plane waves to plane waves. The way that this method works in the context of metagratings is as follows. What we actually start out with, if we want to make a structure that is ultimately either silicon or air, is that we start out with a device that consists of a distribution of refractive indices between silicon and air. So this is an unphysical device that is not binary, but which consists of this distribution. What we then have over the course of hundreds of iterations, so as opposed to thousands from the heuristic optimization methods, is that we basically push each of these refractive index values at each position of this device to be either closer to silicon or air in a way that maximizes the performance of our device until we get a final device that is either silicon or air. So this is to say we do this perturbative modification of every point in our device until we get something discrete. Now, for each iteration, only 2 simulations are required. And this is really where the computational efficiency of topology optimization comes into play, where we only require 2 simulations to basically identify how to perturb many thousands of points within our device. The first simulation is a so-called forward simulation where we have our incident beam and we record the electric field in the device itself. The second is this so-called adjoint simulation where we send in light with an equal magnitude but opposite direction of where we are looking to deflect it to, and we record the field in the device, and we call this the adjoint field. And if you go through the mathematics and utilize certain reciprocity relations in Maxwell's equations, what you find is that in the perturbative limit, that in order to enhance the figure of merit of your device, which in this case is the total transmitted efficiency into our desired direction or into our desired diffraction channel, we can modify our refractive index with a value that is equal to the product of the forward and adjoint fields as simulated through these two simulations. So again, I just want to emphasize here that the key is that with the use of a small number of simulations, we can ultimately perturb the refractive index at every single point in the device. And through this, we can really get tremendous computational efficiency. To show you an example of this, I'd like to play this video of a deflector that was designed to deflect TE and TM radiation to a 75-degree angle with a normally incident monochromatic wave. This is a top view of a single unit cell, and as you can see, we're starting with a dielectric distribution that is random and between silicon and air. And as we let this simulation run, we can see that the refractive index is being perturbed through each iteration, and that through this process, the total efficiency and of light deflection for both polarizations is slowly rising. I should mention that there are a number of bells and whistles that we add to this type of simulation, which is yet another reason to consider using iterative design processes for finding these type of structures. One is that we enforce a minimum feature size into these structures, which is absolutely imperative if we want to actually make this realistically. And the second is that we use a robustness constraint, which basically means that we ensure that not just this device, but devices that are slightly larger and smaller also are able to deflect light with high efficiency. So this is to say we incorporate these constraints, which leads to a trade-off in device efficiency, but which ensures that we're able to actually make this type of device. So when we then benchmark these type of deflectors with kind of the existing conventional methods, what we find with the existing conventional methods is that they work with high efficiencies for modest angles of deflection, but in general, they all have poor efficiencies as we go to really large deflection angles. And for our case, we can really break these limits and get high efficiencies for really this large range of angles of deflection. I should mention quickly, there are a number of interesting schemes for really pushing the efficiencies, utilizing bi-anisotropic media, for example. But many of these analytic schemes work for just a single polarization, and getting large angle deflection for unpolarized light is really a challenge, and certainly it's something that our methods address. Now, at the end, we are experimentalists, and we wanted to see if we can actually experimentally realize these devices. So what we did was we grew polycrystal silicon on an amorphous oxide substrate. We did conventional E-beam lithography and RE etching to produce these type of structures, and we measured the deflection as a function of angle by this very simple setup where we weakly focus light and then mount an optical power meter on a rotation stage. What we see here, theoretically, is that we have relative efficiencies that are in the 90% range and absolute efficiencies in the around 80%. Relative efficiency we define as the deflected light power divided by the total transmitted power, while the absolute efficiency we define as the detected power divided by the incident power. Here we can see for our actual device that the relative and absolute efficiencies are within 10% of our theoretical calculations, which is to say that with these type of robustness criteria, we really can produce devices that can translate experimentally. I should say we've made a lot of devices that don't have this type of criteria, and they perform quite poorly, even though they may work very well theoretically. Once again, with these type of devices, we've decided to use coupled Bloch mode analysis to reverse engineer and understand the origins of these of high deflection efficiency. So what we have here, once again, are the calculated modes in this case for incident TM polarized light, where in this case we have 8 different modes, including many of them which are higher order modes in these type of really irregularly shaped waveguides. And because we have so many modes packed in such a small spatial volume, they necessarily interact with each other. And as we looked at the scattering matrices, we once again see a lot of diagonal and off-diagonal terms, which is to say that indeed these also operate as low-Q Fabry-Perot resonators, where we have radiation coupling into these n different modes, and we do have light kind of bouncing back and forth within this structure. I think one qualitative way you can think about this is that by having these irregularly shaped resonators, we, in essence, can have structures that can support more modes, in essence, giving more degrees of freedom, but that by having more modes in a smaller spatial area, we, in essence, are, these modes then interact more with each other and undergo this inter- and intramode coupling, even though they are orthogonal as they propagate in the metasurface itself, and that it's ultimately the role of topology optimization to fine-tune these modes and these scattering profiles to basically produce a scenario where amongst all of this dynamics, we get strong constructive interference in our desired diffraction channel and strong destructive interference in these other channels. Now, one question that we had was whether all of this inter- and intramode coupling was actually a requirement for high performance. And it actually would be preferable if there are ways to get high deflection efficiency without this type of additional coupling, because it would actually dramatically simplify things. And we can think about this more as a forward design instead of an inverse design problem. But I'd like to show you a quick numeric experiment that we did, which is not a proof, but which is suggestive that actually inter- and intramode coupling is in some ways a requirement. And what we did here was we took for a single wavelength 6 different materials, and we used adjoint-based topology optimization to optimize many hundreds of devices for different thicknesses and deflection angles. And in this case, we're going back to the ridge picture. So we're talking about 2-dimensional deflectors. And so in essence, what we have here are a summary of many tens of thousands of simulations. And we believe, while we can't prove it, that these contour plots represent a near global optimum. We see a number of trends, some of which are obvious and some which are a little more subtle. Certainly, if we are working with lower contrast materials, there are certain limits to overall device efficiency, whereas if we go to really high contrast materials, we can really get high efficiencies for large angles. So that's something that is fairly intuitive. What's not so obvious is if you do go to really high contrast materials, for example, silicon and germanium, then in the case here of germanium, it is possible to identify high efficiency device designs that basically give you high deflection efficiency for these range of angles for a device that's only 300 nanometers thick, which is to say it's only lambda/6 thick. So this is to say that with inter- and intramode dynamics, it's possible with high contrast materials to really reduce the thickness and improve the aspect ratio of these devices, which could be extremely relevant for manufacturing, especially for really long wavelength devices. To ultimately probe the role of inter- and intramode coupling, I'd like to focus on just devices in this case that are made from silicon nitride, titanium dioxide, and silicon, and that have the highest deflection efficiency for 65 degrees. Here we're just picking an angle. And what we find is quite interesting, that amongst all of these simulations, if we look at devices that have high efficiencies for a 65-degree deflection angle, that if we look at these three different materials, the devices actually look very similar. They consist of three ridges, including two narrow and one wider ridge, which seems to indicate that this particular layout is particularly amenable to 65-degree beam deflection for whatever reason. And that as we look at the different modes, they actually all look relatively similar. So this is to say that these devices have very similar layouts and modes, but the difference is that the silicon device has over 90% efficiency, while those made from titanium dioxide and silicon nitride, which have lower contrast, have lower efficiency. And as far as we can tell, the main reason why is due to the fact that with silicon, we do have these additional inter- and intramode dynamics, which are mediated by the fact that the modes here have higher effective indices due to the fact that silicon itself has a higher refractive index, and that these type of devices have much less of these type of interactions, and that as such, for a number of regimes of beam deflection, inter- and intramode dynamics actually is a requirement. I just want to show a couple more images of things that we've done with periodic structures. Certainly one of the advantages of topology optimization is that we can vary the input angle to be not just normal incidence, which is typically what is done, but to also have angles that are non-normal. So in this case, theoretically, we've designed high-efficiency devices that basically take light in at a 20-degree angle, and that can vary the output angle across this wide wavelength range. So this is to say these are nice demonstrations of negative diffraction devices. But as we consider correcting for practical aberrations, such as coma in aperiodic devices, optimizing in ways that can incorporate non-normal angles is important. In this case, here's an experimental demonstration of a device that takes in 50 degrees and that outputs minus 50 degrees. And here we can see for both T and TM that we have relatively high absolute efficiencies. And in this case, what we've done is we've applied topology optimization to make multifunctional devices, which is quite difficult to do with conventional means. Here we are taking in different wavelengths and splitting them to different diffraction orders as a function of wavelength. These are top view SEMs of these devices. Here we can see that as we plot the average efficiency of wavelength splitting per device as a function of wavelength, that these efficiencies scale as 1 over the square root of n. These are experimental values. And that this type of scaling is certainly quite a bit better than the typical 1 over n scaling that is typical of conventional devices. OK, so this is all of the results I've shown so far are for periodic devices. And I think gratings are a good way to really understand and compare and contrast different devices due to our use of, for example, coupled Bloch mode analysis. I'd now like to move to a discussion of aperiodic devices. Because at the end, while gratings are very useful, we ultimately want to apply and our design methods and make useful devices such as lenses and other types. And in applying our design metric to aperiodic devices, there certainly is the challenge of computational scaling. The movie that I showed of the optimization of a single unit cell of the 75-degree beam deflector literally took on the order of 5 hours to run on a CPU, which is to say, if we have a device that is not periodic, it becomes rather intractable, at least using our method, to optimize an entire device. The simulation times become exponentially large. Therefore, we have to figure out a way to break this problem into sections where we're still able to optimize near-field interactions and topology within these structures locally, but which makes this computationally tractable. And our solution has been to design and stitch wavelength-scale building blocks with tailored scattering profiles. So what we do here in this example of a cylindrical lens is that we divide this into linear segments. Each of these linear segments are on the order of a wavelength scale, 1 to 2 lambda. And it turns out that while, in spite of the fact that this is a curved phase profile, that this approximation of it as into linear segments tends to be a reasonable one, as long as this profile is fairly smooth. And we can see here in this case that if we look at this topology-optimized scatter that is on the order of 2 lambda wide, that indeed it is possible, as we start to use topology optimization and incorporate and optimize interactions between these interacting nanoridges, that we can produce these wavelength scale scatters with distinct directions and phase. Here we can see in this near to far field transformation a strong scattering peak to 45 degrees. As such, as we consider something like a cylindrical lens, we can see that if we consider lenses made from silicon nanoridges, that if we consider the conventional approach, where we have nanoridges evenly spaced by around lambda over 2, that the efficiencies are high for small numeric apertures, but really start to drop as we go to larger numeric apertures. And as we look at one such device with an NA of nearly 0.9, we can see, indeed, particularly in this log-log plot, that there's a strong amount of radiation that actually, that especially for large angles, transmits to the forward direction, which is to say that as we go to large numeric apertures, bending light to large angles, as we saw with gratings, is a problem with these aperiodic devices. And just in general, there's a lot of spurious propagation of scattering of electromagnetic waves. But if we consider our topology-optimized devices, the drop-off of efficiency as a function of numeric aperture is much less steep. And here we can see in one such topology-optimized device with an NA of nearly 0.9 that we have much less background scattering, and that indeed it is possible to really have much higher efficiencies by our kind of wavelength scale block stitching approach. Here we have, for these fabricated devices with an NA of 0.6, pretty good agreement between theory and experiment, where we have devices that have focusing efficiencies on the order of, that are within 10% of theory. And we're currently looking to push this to the large NA devices, where actually the challenge is figuring out exactly how to characterize these, because we're actually pushing the limits of conventional off-the-shelf optics. And this perhaps reflects some of the opportunities for meta devices to make high-efficiency large NA devices that do not necessarily exist in practice. Looking ahead, I think the direction that this really needs to go is ultimately to multi-layer structures. And the reason is because with a single layer, there's only so much you can do. You can get a very good phase plate, but it's very hard, for example, to tailor different responses as a function of angle for reasons that are actually quite fundamental to planar structures. Now, certainly, one way you can think about multiple layers is to take conventional devices and to start stacking them. And in fact, there have been some nice studies about that, where people have been essentially designing different lenses and stacking different lenses to make a system. The issue with that, with conventional devices, is that with the limits in efficiency that exist with those devices, the efficiencies of these systems as we start stacking get exponentially worse as we increase the number of layers. However, if we apply topology optimization to essentially design the entire stack at once, we can then optimize the interaction between different types of layers, whether they are in the near field or in the far field. And as such, unlike the case of stacking individually designed metasurfaces, where the efficiencies go down as you add elements, the efficiencies of these devices, at least theoretically, ultimately go up. So just going back to the example of a deflector, if we consider, for example, 10 layers of material, and here it's hard to see, but these are cross sections, we can actually get efficiencies of 99% plus as we go to even very large deflection angles. And not only can we make high efficiency wavefront engineering devices, engineered devices, we can also conceive of other types of devices, such as wavelength filters, both edge pass and band pass type filters, where the response is actually tuned based on the design as opposed to stacks of thin films. By doing this lithographically, you can imagine putting many different types of filters in the same area. Or even something like an angular filter. In this case, we have incident light that transmits for certain angles and that reflects at other angles. And as we do think about these type of structures in the context of computation imaging, I think there really is new type of filtering hardware that we can consider. And finally, I'll just say that while the idea of stacking nanostructures may seem rather intimidating, there are very practical routes to doing this, certainly with MEMS, certainly with interconnects in chips. This is a process that we as a community are actually quite familiar with. So I do believe there are practical routes to really thinking about these meta-optical systems in 3 dimensions that can be practically implemented. And it's just, again, I want to say essential to really think about design routes that can give you high efficiencies through design, because unlike conventional refractive optics, we don't have anti-reflection coatings. And for many of these applications, especially those involving, for example, imaging, we really have to collect as many photons as possible. For the last part of my talk, I'd like to switch gears a little bit and tell you about some of the work we're doing more on the material science front, where I think there's still a lot of really interesting research in plasmonic systems that can be done if we are able to tap and refine materials in the right way. And as we're all familiar with, material properties are a strong function of crystallinity. And if you are to consider, for example, plasmons and their interaction with metal materials, we find that if we have rough polycrystal metal, that in general, the propagation lengths and nonlinear responses are rather limited. However, we are typically limited to polycrystal metal when considering conventional ways of defining nanostructures, which is to say e-beam lithography, depositions, lift-off, et cetera. However, there's been some really nice research recently, which has been showing that if we can really go to single crystal, atomically smooth even metal, that we can then start really getting augmented plasmon propagation lengths, nonlinear responses, et cetera, et cetera. And certainly, a lot of this has been kind of more in the domain of colloidal chemistry. More recently, there have been some very interesting studies of epitaxy growth of thin films using sputtering or MBE. But in general, if we can combine the material quality of smooth single crystal metal with lithography on chip, that could certainly allow us to think about how we make plasmonic systems in the future. Just quickly talking about the colloidal route, this is something that we've been spending, that I've spent some time doing. Here we can see if we want to, for example, make really ultra high quality single crystal gold spheres, that there is a route to do this. We can actually start with single crystal gold octahedra. We can slowly etch in chloroauric acid these type of octahedra until they become spheres. We can see that through this kinetic Monte Carlo simulation that this works because the etching typically attacks the edges and points on these types of octahedra, which allows it to basically smoothen and give us spheres. So here we can see, for example, for traditional citrate stabilized gold particles, they tend to be highly faceted because of the surface energies of gold. But in this case, we have really smooth spheres, and they're extremely monodisperse. We've characterized them. We've done a lot of measurements. They're extremely reproducible. So this is to say, chemistry certainly is a really good route to get extremely high-quality plasmonic materials if we're not trying to make well-defined structures by lithography. Now, if we do want to make high-quality plasmonic structures on chip, we really have to rethink how we do this, especially if we want to make crystalline structures on amorphous insulator like silicon dioxide. And in this case, we've been turning to concepts that are ultimately inspired by bulk metal crystallization. Here, for example, we can see with the Bridgman method that in this context, and this is how a lot of bulk materials are made, you can start with material encapsulated in a quartz crucible. You can melt it into a liquid, and then you can slowly crystallize it by putting it in this temperature gradient. And through this process, you can get crystal nucleation and then crystal growth in a certain direction. A breakthrough came through the labs of my collaborator, Jim Plummer, when he proposed the use of so-called rapid melt growth, whereby some of these concepts could ultimately be scaled on a chip. And furthermore, these type of methods do not require a temperature gradient like these or other zone refining techniques. Rather, this only requires uniform temperatures. And the way this works is that you put, in this case, semiconducting material on a lattice matched or on a crystalline substrate. This here is oxide. You encapsulate it in a microcrucible made out of oxide. You melt it to the melting point of this material. And what you will ultimately get here, due to surface energy considerations, is new crystal nucleation here and epitaxy growth in this direction. So here we can see for indium gallium arsenide, for example, a single crystal. These are EBSD, electron backscattering diffraction images of indium gallium arsenide on amorphous oxide. So the question was whether this could actually translate to metals. And the answer turns out to be yes. And just to walk you through, we have a similar type of process here, where we start with a platinum seed with a gold stripe. We encapsulate it in silicon dioxide to form our microcrucible. We heat it to the melting point of gold. And as the gold cools, it undergoes liquid phase epitaxy, and ultimately we get single crystal metal, at which point we can etch away the crucible. Here we can see in this EBSD image that the yields can be very high. These are all single crystals of gold. And furthermore, interestingly, they all have 1-1-1 orientation out of the plane of the silicon wafer. And that is actually due to the fact that the fiber texture of the platinum seed is actually 1-1-1, even though it is polycrystal. We can see with this high-resolution TEM that we can see very clear lattice fringes that are actually aligned with the oxide interfaces, which do indicate a high degree of crystallinity and strong, again, 1-1-1 preferential orientation out of the plane, which is actually good for example, minimizing electromigration. We've done further study of the precise mechanism, and if you could just bear with me, I know this isn't a material science seminar, but in essence, what actually happens as you heat this up is that the gold and platinum actually diffuse together and form a gold-platinum super solution, a solid solution. And this solid solution actually has, as we see on this phase diagram between platinum and gold, a melting point that is higher than the melting point of gold, which is to say right here. So what we actually have in this case is a solid platinum gold seed, which serves as a site for epitaxy nucleation as the gold melts and then cools. And it's essential in this case that with the platinum and gold having such similar lattice constants that they do produce this eye-like binary phase diagram, and that the lattice spacing of this solid solution is very similar to gold, which allows the liquid phase epitaxy to even work. And we believe that with this understanding of this mechanism, that we can actually generalize this concept to other types of electronically and optically relevant materials, such as silver, copper, and aluminum. And that's something we're actively working on right now. Here we can see in these EBSD images kind of nucleation sites for epitaxy growth. So certainly there's some very interesting material science to be done. I think while there's certainly a very strong motivation to push this towards electronic and optoelectronic applications, that there's really the opportunity to also start thinking about more basic concepts in material science, because this is a nice model system where we can really lithographically define our features and to help and to really specify different regimes of growth. Here I just want to give you an example of something we're working on right now, where we are ultimately creating ideal systems for producing single defects. So here what we've done is instead of having just one platinum seed, we have two platinum seeds. And as we heat this up and liquefy the gold and let it cool, we actually get now two crystal growth fronts. And as these two crystal growth fronts propagate and ultimately meet in the middle, we have a single grain boundary. So in this case, we can see from EBSD and high resolution TM that we can produce really high quality bicrystals with extremely clean grain boundaries. Talking to people in material science, it turns out to be a real challenge to do things like produce very well-defined single defects in, for example, bicrystals. And it's not just looking at single grain boundaries, but potentially situations with other types of with multiple grain boundaries, ways of controlling a crystal orientation. Certainly as we start understanding very fundamentally the role of individual defects in the optical, electronic, thermal, and mechanical properties of metals, this is a very interesting model system. And certainly I believe some of that will help us further understand how these materials work in the context of optoelectronics. Okay, so to summarize, I hope I've convinced you that topology optimization is the foundation for multifunctional large NA metasurfaces. And it certainly is, I would say, maybe an obvious statement that optimization is a route to produce high efficiency devices and to improve the performance of devices, of conventional devices. But I think one of the key points that I want to make is that we're not just making optical phase arrays better, but we're really accessing regimes of the design phase space that really are not accessible through conventional means, and that as we really look to making really highly complex devices that are, for example, aberration corrected and that have very high efficiencies, that there is just no other way to access those areas of design phase space. there's still some major challenges. I think managing computational requirements is a big one. And as I mentioned, this is, even though it's very computationally efficient, it's still very computationally taxing. So we're really looking into using, for example, machine learning algorithms. GPU computing, I think, will be big as we push the simulation speeds of electromagnetic solvers in general. Figuring out efficient ways of incorporating aberrations, because we do want to make practical devices that, and we're still far from what we can do with refractive micro-optics. I mean, that's an area that's extremely well developed. And certainly thinking about scalable fabrication. And then the last part of my talk, I think, while there's a lot of interesting things to do with dielectrics, that there's still a very bright future for plasmonics. It's more a question, actually, of materials limitations. I'd like to thank my group for this effort. For the topology optimization, a lot of the work was done by my former postdoc, Jianji Yang, David Sell, currently Peter Fan, Sage Doche, and actually UW alum, Evan Wang, have been continuing to really make great strides. And for the single crystal metal, Ray Yang and a new postdoc, Rachel Traylor, have been really pushing that. So with that, I'd like to thank you for your time.
So any questions for John? So when people are thinking, so one thing I wanted to understand, so you said the lower index has less deflection, and I have read the paper, but you said that it's because there is more coupling in silicon, and that part I did not understand, because my understanding was that if silicon pillars are high index, so there's less coupling between pillars. Like if you think about, like the light is confined in the waveguide. So can you?
Sure.
Yeah.
Yeah, so I would say in the conventional picture where we think about, here, let me just pull this up. Yeah, so the question was whether was that with high contrast materials like silicon, there should actually be less coupling between pillars. And certainly in the conventional picture where you have kind of discrete waveguides, there certainly will be less coupling between the pillars. And that could actually be a mechanism to packing them closer, which is actually a way with conventional device design you can think about improving performance. But I think the difference here is that these structures are ultimately coupled to begin with. So there's actually strong coupling, or as we can see, these modes are actually spatially distributed across, all of these pillars, which are pretty closely spaced. So that, so this way of thinking about kind of coupling between pillars doesn't quite apply here, and that these modes, as they are all spatially distributed, do couple together as they interact with the different interfaces of the metasurface. So there is ultimately a qualitative distinction between enhancements in kind of conventional high contrast materials versus what we are seeing here.
And this coupling is between unit cell only, right?
Well, these are Bloch modes.
Okay, yeah. Okay.
So these extend out to infinity, okay. And here everything involves periodic boundary conditions. Yeah.
Alan?
So in general, when you're dealing with gradient-based methods, sometimes you run into local minima.
Sure.
In your experience, do these local minima tend to be good enough, or do you have some way of getting around the local minima?
Yeah, you're absolutely right that these are in essence gradient descent methods. So you are just in a local space. We've taken certain measures to try to get out of this space as much as possible. I didn't actually mention it when this movie was being played, but these very sharp dips in efficiency as these structures are blurred actually is our way to kind of kick out of local minima and to further explore larger areas of the local design space. So I think there are ways to kind of manage this a little bit. What I will say, which I think is kind of interesting, is we've done this a lot, and we've looked at many thousands of results from topology optimization, is that even for a single type of function, it turns out that you can often have a number of solutions that look very different, that have high performance and high efficiencies. So, so this is to say that we don't have to look for a needle in the haystack, so to speak. There are actually a few needles in the haystack, and this method seems sufficient, at least for basic beam deflection, functions, to be able to find some of these needles, given a few random starting points and a few topology optimization runs.
Any other question? Yeah, if not, I think it's already past 11:30, so let's thank the speaker again.
All right, thank you.